Alright, so in this question, I'm probably going to be talking more than I am actually writing, because almost every question is an explain, not a calculation. But there's something I'm going to be drawing, so it'll be some value, but it's going to be a bit blanker screen than normal. This type of question, however, is really representative of a wave type of free response on the Physics 1 test, precisely because it's so based on your ability to explain a concept and not your ability to exactly do a calculation. So what I am saying is absolutely critical for you to be writing parts or most or some rewording of that on the page. Right, just an equation alone will not show you enough, or not show enough to the examiner. You have to explain sort of every little detail. So, with that said, here's kind of the process. So we're given 4 different strings attached to an oscillator, and we adjust the frequency of that oscillator until that string is vibrating at its fundamental frequency. And in doing that, we find that all 4 strings have a different fundamental frequency. So just drawing one of the setups as a guide, right? We have string goes over a pulley. We have mass M hanging on it. And we have our oscillator attached to the other end, right? And so we find that the 4 frequencies, the 4 fundamental frequencies are 400 hertz, 382 hertz, 364 hertz, and 350 hertz, right? Those 4 strings, 4 frequencies. And we're also told, I forgot to label this, that the vibrating length of the string is L. And the AP test gives us an additional equation here that's not on the equation sheet. So we have to remember how to use it, but right, if we may not always be given this equation. We're told that the velocity of the wave is the square root of the tension force divided by the mass divided by the length. Right, and then all that's defined. So this is an equation that we've used in class, so hopefully you're familiar with it. And so the question part A is, what is different about the 4 strings that results in them having different fundamental frequencies? And so we have to pair this equation with one that is on the AP sheet, which is a relationship between the wavelength and the frequency. So, these 2 equations and the data we have will be all we need to actually put these pieces together. So the next step is to note that a fundamental frequency is a statement about wavelength, right? If we draw the wave on here, the fundamental frequency, right, the standing wave is going to look like this, right? It has nodes at both ends and nothing in between. So this tells us that even though the fundamental frequencies are different, this is the same for every single wave, right? That's the definition of the fundamental frequency. So if the wavelength is the same for everything, but the frequency are these 4 different numbers here, then that tells us something very important, that this different, right, the speed must be different for every single one, right? The thing with the highest fundamental frequency has the highest speed. So if I was going to write this, I would be writing something like, the fact that the fundamental frequency has nodes at both ends and only one antinode total tells us that we have exactly half a wavelength on each of those strings. That's the same for all of them. Since they all have different frequencies and the same wavelengths, this equation means that all the wave velocities must be different. Right? So now we've established that all the wave velocities must be different. Now we can look at the equation about the velocity. we are told that they're all string length L. Right? This is the same for all. And because this hanging mass is the same, the tension force must be the same. Right? And so we've established that this is different. That's this piece. I'm going to draw that a bit differently. That's this piece. So for V to change, if these two pieces are always the same value, there's only one thing left. There's only one thing left to consider, and that's the total mass of the string. So the only way that they can have different velocities of the wave is if the strings have different total masses. And so my conclusion is, what's different about the four strings? The mass of the four strings must not be the same, because that's the only thing that can be different to change the wave speed. And we know the wave speeds are different because the wavelengths must be the same, because it's always the fundamental frequency, and the frequencies are all different. Right? So that's part A. Part B is pretty similar. It's just a combination of these two equations, just precisely. So if I were doing this, the first thing I would do is I would combine these equations. So I have velocity equals for both, so I'm going to get lambda times frequency equals the tension force divided by the mass divided by the length. And we're making a plot of frequency as a function of mass density, which is this thing. So I'm going to replace that with mu, just for simplicity, rather than leaving both variables. So we want frequency equals, that's what frequency as a function means. So frequency equals 1 over lambda square root of ft over mu. So we're plotting, right, we plot frequency, so this is our, actually I should write it a different way. So we're plotting frequency, which is then the y variable is frequency. And that's frequency as a function of the inverse of the linear mass density, right? The inverse of the linear mass density. We plot f and 1 over mu. And the question is, would that be linear? Well, look at our graph. We have f as our y variable, so that's good. But here, this linear mass density is under a square root. So these aren't, right, this is not the same thing. We'd have to plot the inverse of the square root of the linear mass density for it to be linear. So I would write this equation, and then I would state something like that the equation has the inverse of the square root of the linear mass density, not just the inverse of the linear mass density. Therefore, it's not a linear relationship. Right? The biggest key is combining those equations. The second biggest key is sort of knowing how it relates to that linear function to explain. Okay. So finally, we have part C. So part C, we've changed one of our oscillators and one of our frequencies that we're oscillating at. That's right. So we have our table. That mass doesn't change. Our oscillator still is there. But now we're doing 700 hertz. And we're told that this is the second harmonic. Right? And if you go back and look at string D, you see that 350 hertz times 2 is 700, so it's consistent, right? But we're told that anyway. They technically wouldn't have had to tell you it was the second harmonic. You could know that from just the fact it was 700 hertz. So we have a couple different points on that string, right? The one right there, the two ends, and then it's sort of divided up into parts. Let's see if I can get this right. So kind of like this, I think. Oh, that's 11. There's 12. Yeah, so they should all be evenly spaced, but obviously that's kind of hard to do without a precise ruler. So they're evenly spaced tick marks. I'm gonna see if I can do a better job. So 1, 2, 3. Okay, that's a little bit better. All right, evenly spaced tick marks, and we have to figure out the points on the string that have the greatest average vertical speed. So the waves are traveling, right, like that direction, but the string is oscillating up and down. So the statement of the greatest average vertical speed is where are the antinodes, right? Those are the things that move the most in this up and down direction. So that's all we need to do. We need to find where are the antinodes. Well, we know what the second harmonic looks like. There's a node at the end, and a node at the end, and a node in the middle, right? And so the wave looks kind of like that, right? And so the antinodes are exactly the midpoints of the nodes. So this is L over 2, so the antinode happens at L over 4, and so that one is this, again, if I drew it perfectly, which I clearly have not, but it's this, it should be the tick mark like right there. Yeah. Yep. And similarly, this one, right, the mid of that is that one right there. And so, right, I drew a lot of extra stuff on it. All you really need to do is what I'm going to sort of redo in green is on the string, so I'd put a little like dot kind of like that and kind of like that. That's really all your final answer is just those points, right? You don't need to indicate where the nodes are. You don't need to draw that standing wave that I did in blue. But if you do that, that really makes it easy. So all that kind of work should be something that you do to kind of help you out. All right? So not a whole lot of calculation on this question, right? It's very much about remembering some definitions and knowing relationships and the rules of standing waves and a lot of written explanation.